Welcome, everyone. It's really a great pleasure to see so many of you joining today. Thanks a lot for joining early, being all muted, and thanks a lot for watching the talk and making sure you ask questions and interrupt the speaker when he's going too fast or the talk is confusing or you have a question to ask. So it's a pleasure to have Swastik Kopparty today give the talk from Rutgers. Before I introduce Swastik properly, let me maybe go around the table and see if I can figure out who's joining us today. So we have a group in India or Madhav, a group from a group from Northwestern. Welcome, guys. Then we have Clément Canon and a group joining us from Columbia University. Then Dimitris Paparas is joining from University of Wisconsin. Dylan McKay is joining from Stanford. Welcome, guys. Jia Peng is joining from UCSD. Welcome. Then we have a group from Caltech joining with Piyush. Shravas is joining us with a group from CWI. Welcome. Then we have Sina joining from University of Michigan. Vishwajit joining us from IIT Madras. You joining us from University of USC. And last, I'm sorry, I can't read your name because it's in Chinese characters for me. So this might be Yongsan Lin from Purdue, is it? Yeah, excellent. So we have Yongsan joining us from Purdue. Okay, so that's everyone. So welcome, guys. So before we start, let me thank everyone who's helping behind the scenes. Clément Canon and India Day, Oded Regev, Gautam Kamat. You can't see them right now, but they're doing all the work. Also, let me announce the upcoming talks. So 2 weeks from now is a bit special because the Wednesday would have fallen right after Fox. So we're skipping that session and instead having it the week right after. So the next talk will be 3 weeks from now. And sorry, and I forgot what is the next talk 2 weeks from now. So this will be on October 19th, and Ronan Eldan will be giving the talk. And then we'll have a talk the week after, October 26th. And then it'll resume every 2 weeks. So we'll send email about this. All right. So it's a pleasure to have Swastik Kopparty to give the talk today. So Swastik got his PhD with Madhusudan at MIT 2010. He's now at Rutgers University. He's done a lot of great work in complexity theory, especially coding theory. For instance, list decoding of all kinds of codes, and also properties of locally decodable, locally testable error correcting codes. And I think this is what he's going to tell us about today. So welcome, Swastik, and thanks for giving the talk.
Oh, great. Thanks. Thanks very much for the invitation. And also thanks to all the organizers for running the series. I think it's a great service to the community. Great. So I'm going to be talking about high rate local codes with subpolynomial query complexity. This is joint work with Or Mair, Noga Ranzevi, and Shubhangi Saraf. Please stop me when you have any questions. Yeah, so right now, as far as I know, I'm talking to myself, so it would help if somebody does interrupt occasionally. Okay, good. So I'll start with a review of what error correcting codes are. Good. So we have a finite alphabet sigma, and for all practical purposes, a code is just a subset of sigma to the n for some very large n. Okay, and what makes it interesting from our point of view is a distance property. So if every pair of code words within C differ on at least delta fraction of coordinates, that means their Hamming distance is at least delta n, then it has the distance property of every code word. We say the code has distance delta. And so the picture to keep in mind is that it's just a bunch of well-spaced points within sigma to the n. Okay, and when you have such an error-correcting code, there are some basic algorithmic questions that arise when working with these codes. And so the three tasks that I'll look at today are, so there's encoding, decoding, and testing. Encoding is just a way of mapping, finding a bijection from a set which you know, like sigma to the k, to the set of all code words in the code. Another algorithmic task is the problem of decoding, which is given a string in sigma to the n, which is close to a code word, the problem is to find the close by code word. And testing, which is to detect, given a string in sigma to the n, to tell if is there a close by code word. The utility of error correcting codes for the problem of error correction comes from the following simple observation. Given a collection of points which are all delta apart from each other, if you start with the code word C, and then it gets corrupted in a small fraction of coordinates, and maybe you get a string R in sigma to the n, which is no longer a code word, then the code word C is still going to be, I mean, you can identify what code word C you started with, because it's going to be the unique C which is very close to R. And this follows from the distance property of the error correcting code. And the decoding and testing problems, the algorithmic problems, are what arise when you try to use error correcting codes to error correct. Great. So this is the theory. This is the very basic definitions underlying error correcting codes. The study of error correction is very, very old. It started in the 1940s with Shannon and Hamming. Much has been studied since then. So today we know lots about error correcting codes. In fact, we've known for many, many years many things about error correcting codes. We know how to get error correcting codes with which have efficient encoding, efficient decoding, and furthermore, the two parameters of interest in this problem, namely the distance delta. The distance delta is constant, and furthermore, the rate of these codes is also constant. The rate here measures the ratio between the number of measures the ratio between k and n, as in the definition of bijection. So you have k symbols from your alphabet got encoded into n symbols of your alphabet, and the ratio between k and n is known as the rate. It's a number between 0 and 1, and higher rate means that there's less redundancy in your encoding. So we know efficiently encodable error correcting codes, efficiently decodable error correcting codes, and this can also be done in linear or near linear time. So much has been achieved towards the very basic questions of error correcting codes, which is to come up with constructions of error correcting codes for which we can do our basic algorithmic tasks efficiently. Good. Even more is known. We know we are also able to do all this simultaneously with achieving optimal rate distance trade-offs for these codes. So for as long as the alphabet size is large, we can even do all the above with rate and distance having the optimal possible trade-off amongst all error correcting codes, namely with rate and distance, rate plus distance equal to 1, the relation R plus delta equal to 1. Okay, good. So a lot is known about error correcting codes. In many talks, you hear, oh, when you have a problem which you cannot solve, what should you do? And the answer is ask a different problem. Okay, so we are here in a situation where you have a problem which you can solve, namely the construction of error correcting codes. So what does one do in such a situation? Anyone? Feel free to answer. I think this is a good time for someone to answer. Okay, fine. So let me just tell you. The answer is you ask another question. So the main question that we'll be looking at this talk is, so even though we know how to do so much with error correcting codes, there is still another very interesting question that one could ask about this, which is what can be done in sublinear time. Everything about encoding and decoding that we know, and we know a lot, can all be done in linear time, and from the point of view of deterministic algorithms, this is basically as good as you can hope for. But given so much that can be done with randomness in other situations, it makes good sense that we would ask what can be done in sublinear time. Okay, and this question was asked in the early 90s, and many people have studied this question since then, and there's a lot of interesting work on these topics. Good. Okay, so that's what we'll be doing. What can be done with sublinear time with error correcting codes? So the plan of the talk is the following. I'm going to first say what the objects that we'll study are. These are locally decodable codes, locally correctable codes and locally testable codes. I'll then tell you a little bit of what's known about them. Everything in this talk will be about codes in the constant rate regime. So I won't be talking about many of the very interesting things that have been done in the constant query regime, but I will tell you about what all is known for constant rate error correcting codes with local algorithms. And then I'll tell you about the main result of this talk, which is an improved query complexity, LCCs, LDCs, and LTCs with improved query complexity, and also with improved rate distance trade-off at the same time. And I'll end with some questions. Oh, so okay. So any questions about what we're going to do? Okay, great. So I'll yeah. Okay, great. So let me introduce the main definitions for this talk: local testing, local decoding, and local correcting. So the local testing problem is the following: it's a weakening of the standard testing question, where we don't ask a hard decision question, but we have some promise in the middle. So we're given a string r and sigma to the n, and we're asked to distinguish between two cases which are well separated. One of them is the case when r is in the code, and the other case is when r is far away from the code. The distance of r from c is greater than epsilon. Okay, and the problem is to do this as quickly as possible. And since we have a distinguishing question of this form, it's reasonable to ask, can we do it in sublinear time? And this will be the question. Another interesting question here is the local decoding question. It's a way of asking an algorithm to decode a given received word, which is say a corrupted code word. You want to decode it to the nearest code word, but in order to formulate it as a problem which you can solve in sublinear time, you can't ask for that code word, because the code word itself is so big that you can't hope to do it in sublinear time. So instead, the version of the question that we ask is that decode it to the nearest code word. Then, that code word came from some message. Tell me the ith bit of that message. Okay? And that's the question. So given r in sigma to the n and a coordinate I from 1 to 3 up to k, if there is a message such that r is close to the encoding of that message, return the ith bit of that message.
So this is not the same. Maybe this is going to be your next point. I'm sorry. I was going to say this is not the same as recovering just some coordinates of the nearest code word, right?
Right, exactly. So this is there's a slightly different notion which is called local correction, which is to output coordinates of the code word. This is local decoding, which is to output coordinates of the message, which was before you did the encoding. And both of these are these are slightly different questions, and in some settings they make a difference. So local correcting is the notion. You're given a string r and sigma to the n and a coordinate j in 1 to 3 up to n now. Remember, k was the number of message symbols, n is the number of code word symbols. And the question is, if there is a code word which is close to this received word, find the jth coordinate of that code word.
So
it is often, yeah.
Yeah, I've got a question about the local testing. What kind of like epsilon is here? Like, is it like between like the distance over two, or like, or any range is fine, or is there like a particular range for which it makes sense?
So this is a good question for many choices of epsilon. So if epsilon is bigger than, say, the covering radius of the code or something, then this is a meaningless question. But it's already interesting when epsilon is say distance over 2, and it's especially interesting when it's much smaller than half the minimum distance, but still constant. So maybe delta over 1,000 or something like that.
So in terms of the parameters, so like we have n and k will be like linked to, like, related, but what should I think of? Like k goes to infinity, then sigma, the size of the alphabet, goes to infinity, and then epsilon is small but constant, or like what's the...
Good. So there's going to be the codes will have some distance delta, and so delta is growing in some fashion. The ultimate goal of what we would like, say, are codes with constant rate, constant distance. So delta is a constant, and then epsilon will also be some other constant less than delta, say, or less than delta over 2. For the testing question, and for decoding, epsilon certainly has to be less than delta over 2 for you to be able to hope to find the correct answer. Yeah, and so this would be a good setting for
Thanks.
For these parameters. Good. So, and in all these questions, the goal is to use as few queries to R as possible. This is the point of this formulation. We had a bit of promise in we're asking. I mean, the local testing question, you're guaranteed that either R is in the code or R is far from the code. And in the local decoding and correcting questions, we're only asking for a result in case R is close to the code. And in other cases, we don't ask for anything. And the question is to use as few queries to R as possible. And of course, this is going to be a randomized algorithm, and it should succeed with high probability in all these cases. Okay, and in all the settings that, when we look at these kinds of questions, we always assume epsilon is a constant. So when you locally decode, you correct a constant fraction of errors. And this is what we mean. This is why we can start ignoring this epsilon parameter when we talk about when we talk about trade-offs between rate and query complexity and things like that. Because this is a convention that these are the kinds of codes that we want. Okay, good. So I'll quickly draw pictures that show what locally testable codes do. It's basically just saying the same thing, but I also draw a picture at the same time. So you're given a string R and sigma to the end, and you're trying to answer is R in C. And a local tester is an algorithm that queries, it tosses some coin, that queries a few locations, and it outputs either accept or reject. And if R is in the code, it always accepts. And if R is not in the code, then it rejects with some probability, say proportional to the distance of R from C. So there are various ways one can formalize this definition. Both of the things that I said are different formulations, and both are interesting. Locally decodable codes, again, so we have a string R in sigma to the end, and we're given, so our local decoder algorithm is given a coordinate I in 1 to 3 up to k, and based on I, it makes some queries, and it outputs the ith symbol. It outputs mi, which is supposed to be ith symbol of the original message. Locally correctable codes, very similar, except now the I that you get is a coordinate from 1 to 3 up to n, and you output the ith coordinate of the true code word. Okay, and locally correctable codes are, as long as the error correcting codes that you're working with are linear, which means that the code words all form a linear subspace of some vector space, then every locally correctable code can be made into a locally decodable code. So if you construct a locally correctable code, you've automatically constructed a if you've constructed a linear locally correctable code, you've automatically constructed a locally decodable code. And so for the rest of this talk, I won't talk about local decoding anymore. Everything I do will hold for locally correctable codes, and all the codes will be linear. So we don't need to talk about local decoding.
So I have a question.
Yeah.
Are you going to talk about applications? What are some settings where you might be interested in finding some bits of the message or the code word, but not the entire?
Good. So this is actually a very good question. So the original reasons for studying locally testable codes and locally decodable codes were complexity theoretic, and they had nothing to do with the applications, but there were some very strong applications for these. They had nothing to do with real world applications, but there were some very strong complexity theoretic applications for these objects. But there's also a very good real world application that one could imagine. So you have a whole bunch of data, maybe all the email of Google or something like that, and you want to store it in some way so that it's robust to errors. So even if some epsilon fraction of your database gets corrupted, so your encoded data gets corrupted, you can still access one particular email. You shouldn't have to decode the entire database of everything you've stored just in order to access a tiny bit of information which you know is hidden in there. The current way this problem is solved is to break your data up into teeny tiny blocks and use an error correcting code separately on each block. This is great, but it loses this resilience to a constant fraction of errors. If you take a gigabyte of data and break it up into bytes and encode each byte into 2 bytes, then all it takes is 2 bytes to disappear for for some data to be lost. And yeah, so this is imagining a scenario where you can protect all your data from a constant fraction of errors and still retain easy access to a single part of your data, yeah, while it is still robust to errors.
I've got another question. So here you said that there was basically a reduction between LCCs and LDCs.
Yeah.
There is no such. Is there a relation between LTCs like testable and correctable, or no?
No, there's no known relation. In fact, the parameters in which they're known to exist are quite different, and there's no known relation. And in some cases, it's known that there are some rate distances that can be achieved for rates and query complexities that can be achieved for LTCs that cannot be achieved with LCCs. Yeah, but they do show they are friends of each other. So in constructions of locally decodable codes, you may use a locally testable code as a piece, and in constructions of, and the other way around. So they're friends, but they're not equivalent. Okay, so any other questions before I continue? Okay, great. So I'll carry on. I'll just say very quickly some motivations for studying these objects. For local decoding and local correction, there are many applications to cryptography and complexity theory. Some of these are not applications; they're just connections. But yeah, there's a lot of import-export with other core areas. The mathematics behind these objects is very, very interesting, both in the construction of these objects and that the ideas that go into the construction of these objects, as well as the ideas that go into understanding and proving limitations of them. And finally, I mean, this wasn't the reason why they were defined, but potentially this could be interesting for practical coding theory, where you actually store data using error-correcting codes. It gives the possibility that all your data is stored as is encoded as one code word, and then you can still access individual bits of your data very easily while protecting it from errors, instead of breaking things into blocks, which then loses the resilience to a constant fraction of errors. For local testing, again, the original reason for studying them was very complexity theoretic, and there are many connections to those subjects. It's also mathematically very, very interesting. And again, this has the possibility of use for coding theory in practice. Good. So before getting into any discussion of what we know and all the recent stuff, I want to start with the most important local code of all. These are the Reedmuller codes. These were the codes that started off. All studies into local codes in the early 90s, and they're very, very. It's a very, very good example, and it's a good example of where this locality phenomenon comes from. Okay, so I'm going to define an error-correcting code now. So you have a bunch of parameters. So I'm going to look at m variable polynomials over the finite field fq of degree at most d. Okay, when I talk about degree of polynomials, I mean total degree of polynomials. Okay, so we have, so we are looking at multivariate polynomials of degree at most d over a finite field fq. And we'll assume that d is bounded away from q. It's smaller than q. It's something like 1 minus delta times q, where delta is some constant. Okay. This gives us a code which is take any such polynomial and look at its evaluation table on all of fq to the m. Okay, it's an m-variate polynomial over fq, so you can evaluate it at points of fq to the m. So do this evaluation. So you then get strings of length q to the m over an alphabet fq. Good. So that's what the code C that we just defined. These codes are called the Reedmuller codes. Okay, and one can calculate the dimension of these codes as a linear space over fq. It's d plus m choose m, which is the number of monomials of degree at most d in m variables. Okay, so having done this, one can now compute the rate and the distance of these codes. The rate of these codes, one can, this point is just a calculation. The rate is about 1 over m factorial times 1 minus delta to the m. So we take delta to be some constant like 0.1. This is something that, yeah, so it goes exponentially fast down in m as m grows. And the distance of these codes is delta. And this is a consequence of the Schwarz-Zippel lemma, which says that polynomials of low degree cannot have too many zeros, which also implies that polynomials of low degree cannot agree on too many points. And that's what gives the distance property of these codes. Okay, so so far we've said nothing local. Everything I said was about, it was just the definition of a code. Now let's also see a little bit about where the locality in these codes comes from. The main observation is that if you have a polynomial of, if you have a multivariate polynomial of degree at most d, then any restriction to a line is it gives you a univariate polynomial of degree at most d. And this is some kind of local structure that's sitting inside your code word, and it can be used for testing and decoding. Okay, so the local testing, the main local testing result about Reedmuller codes, this is a theorem of Rubenfeld and Sudan from very long ago, says that, yeah, Reedmuller codes are locally testable with some parameters. And the local test is the following. Pick a random line in FQ to the M. Look at your received word R and restrict it to the line L. This ought to be a polynomial of degree at most d. If the original string had been a true code word of the Reedmuller code, this restriction should be a univariate polynomial of degree at most d. So the tester just tests that this is actually the case. The fact that this works is quite non-trivial. Yeah, quite non-trivial. But it does work. It's a very nice and beautiful theorem. I highly recommend looking at it if you haven't seen this. Let me also now talk about the local correction. In the local correction problem, you're given some function r from fq to the m to fq, and you want to recover the value at a point x in fq to the m. Yeah, so here there's another natural algorithm. One picks a random line L passing through the point x, query the received word R on that line L. It ought to be a polynomial of degree at most d. Since it, so if it is, then good, then that means we can deduce what the value at the point x ought to be from this. And if it's not, well, maybe find the best fit univariate polynomial of degree at most d on this line, and the polynomial that passes through as many points as you can, and then output its value at the point x. Okay, so this is the algorithm. It actually works. Analyzing it is much easier than the analysis of the local test, but it's still not totally trivial. So this is a good exercise if you understood exactly what the local correction procedure was. Okay, good. And in both cases, the query complexity for the local algorithm is the number of points on a line. The number of points on a line is q in fq to the m. So the number of points on a line is q, which is the mth root of the total number of points in the whole space. So the query complexity is the mth root of n. So, and it improves as you increase the number of variables m. But as you increase the number of variables m, you pay for it by reducing the rate exponentially in m. So this is something to be aware of. Okay, so just to summarize, out of Reedmuller codes, for a constant, for any constant beta, you can get codes of constant rate, constant distance, and which are locally correctable and locally testable with n to the beta query complexity. And beta here is just 1 over n. Good. So these are Reedmuller codes. These are these are all future local codes in some way are inspired by these codes, and yeah, they're very, very basic. It's a very basic example, and it's very, very inspiring. Okay. Let me quickly say that in the constant query setting, locally correctable codes, locally decodable codes, locally testable codes are very extensively studied. There are many, many interesting and deep results in this setting, and there are many, many open questions that are unanswered. But I won't talk about anything in this, any of these things in this talk. Good. Instead, so now I'm going to focus only on the constant rate regime. So we're talking about codes of constant rate and constant distance, and we're trying to understand what's the smallest query complexity that you can have. So an old result of Katz and Trevisan says that if you want a locally correctable code or even a locally decodable code of constant rate, it must have query complexity at least omega log n. You cannot have constant query codes with constant rate, for example. Okay, so in this setting, so we're focusing exclusively on constant rate. In this setting, the Reedmuller codes achieve rate being much smaller than exponential in minus 1 over beta. That should have been exponential minus 1 over beta. Yeah. And query complexity order n to the beta. Recently, since 2010, there has been progress which showed that one can improve on Reedmuller codes. One does not need to trade off the rate with the query complexity. It's possible to have for every rate less than 1 and for every beta greater than 0, a code with rate r and query complexity n to the beta. There's just no relationship between between r and beta whatsoever. There is some trade-off, but that trade-off goes into the distance. The distance of the code ends up being r times beta, which is still a constant. So for any r and beta, there are constant distance codes which there are constant distance codes which achieve rate r and query complexity n to the beta with no trade-off between r and beta whatsoever.
And are these they're based off Reedmuller codes? Are these multiplicity codes or something like?
Yes, that's right. So in fact, this result has been proven 3 times by 3 completely different families of codes. One of them is multiplicity codes. Another one is lifted Reed-Solomon codes, and another is expander codes. The first 2 are very closely related to Reedmuller codes, but they're quite different from each other. And expander codes are quite different from everything, but there are some similar undercurrents to Reedmuller codes. And so it's quite surprising to me, at least, that so we have 3 different families of codes that all go beyond Reedmuller codes, and they all achieve exactly this trade-off: arbitrary rate, arbitrary beta, and query complexity n over n to the beta and rate r less than 1.
Oh, and there's no matching. There's no lower bound for this.
No,
you should have this r beta. Oh, okay.
Oh, right. We don't have a matching lower bound for this, but I mean, the three codes that that show this, then surely there should be a matching lower bound. Good. Hold on to that thought. Let me now shift from LCCs to LTCs. For LTCs, there's a burning open question, which is there could be constant rate 3 query locally testable codes. We do not know how to rule this out. This is a big shame, but it might be because they do exist. Okay, it is known how to come very, very close if you're really willing to relax the constant rate requirement. If you're okay with rate being 1 over polylog n, then results of Ben-Sasson-Sudan and Dinur imply that you can get locally testable codes with 3 queries and rate 1 over polylog n. So this is very, very, very close, but it's not there, and this is a very interesting open question. If we insist on constant rate, though, the query complexity blows up much more. Then Reedmuller codes achieve rate being, again, it's the same error. Let me fix it. Fine. Reedmuller codes achieve positive but very small rate with query complexity O n to the beta. And here too, we have progress from the last 4 or 5 years, which go beyond Reedmuller codes, and it's exactly the same kind of behavior. For rate less than 1, for every beta greater than 0, with no relationship between R and beta, one can get locally testable codes with rate R, constant distance, and query complexity O of n to the beta. And this is achieved by 2 different families of codes. One are tensor codes, which is a family of codes introduced long ago by Ben-Sasson-Sudan, but only used in this context by Widerman after an improved technical result. and also the lifted Reed-Solomon code. So lifted Reed-Solomon codes were in both these categories, for LCCs and LTCs too. Good. So, so to summarize, it seems like for constant rate, for any constant rate, one can achieve n to the beta queries. Well, not you see, it's true that for any constant rate, one can achieve query complexity n to the beta with no trade-off between rate and beta. But all these constructions break down when you make beta go less than constant. At the moment it's less than a constant, then the distance of the code becomes sub-constant, and then oops, that's illegal. We don't count those as locally testable codes and locally correctable codes. Okay, good. So given all this, given that there's so many different codes achieving exactly the same set of parameters for both these problems, I think it's a very, very reasonable question. Do locally correctable codes and locally testable codes with subpolynomial query complexity exist? And everything from before strongly suggests no. And why? Because you have a bunch of different ideas. All of them seem to say something interesting because they're going beyond Reedmuller codes, and all of them fail at exactly the same point. Okay, and so having said all that, so the main result of this talk, if you remember the title, if you would know this, the main result is that yes, they do exist, and we'll see in this talk one tool that will help us go beyond for both locally correctable and locally testable codes, and then I'll talk about some more ideas that can further improve the query complexity to small subpolynomials. Okay, good. So that's what the rest of this talk is about. Any questions about what I said so far? Okay, good. So then I'll start with the main result for locally correctable codes, and I'll outline. So I'll give some details about the proof here, and then for the locally testable codes setting where the theorem is slightly stronger, I'll give a sketch of how that is. Okay, so for all, the main result for locally correctable codes is that for every rate and distance with rate plus distance less than 1, there's a family of codes of rate R which is locally correctable with n to the little o1 queries from a constant fraction of errors. So there are two improvements in this theorem over what was known before. One is that the query complexity went subpolynomial, and the second is that the rate distance trade-off is now optimal. It's for every R and delta with R plus delta less than 1. In other words, these codes approach the singleton bound, which we didn't know before for any query complexity. Okay, and the exact subpolynomial behavior is 2 to the root log n log n. So it's not polylogarithmic, but it's halfway there, I guess. Good. The main result for locally testable codes is very similar. It's for, again, the rate and distance trade-off approaches the singleton bound, and they're locally testable with n to the little o1 queries from constant fraction of errors. So right, and here the query complexity we can further improve to log n to the order log n. So this is not polylogarithmic either, but this is at least quasi polylogarithmic, while the previous one was super quasi polylogarithmic and subpolynomial. Good. So I'll now give in detail the construction of the locally correctable codes. Okay, so the main construction has two components. The first one is high rate codes with subpolynomial query complexity, but which only tolerate a sub-constant fraction of errors. So this is related to what I said earlier on. I said, oh, we always insist that locally correctable codes have constant you can correct from constant fraction of errors. That's why we never mentioned the fraction of errors when we talked about it before. Okay, so I'm going to violate that and say, okay, so now let's pay attention to the fraction of errors. And the first ingredient is to construct high rate codes which tolerate only a sub-constant fraction of errors. This is a weaker requirement, so it's reasonable that, oh, maybe now we can reduce the query complexity further. And the next component is called distance amplification. It's to take a code which is only resilient to a sub-constant fraction of errors and transform it to improve its distance to a constant fraction and make it resilient to a constant fraction of errors. Question? Someone has a question?
No, I think it's okay. There was a. You can go ahead.
Oh, okay. And the second component, the distance amplification, will lead to the new query complexity being polynomial in the old query complexity and 1 over delta naught. So it's not enough just to get subpolynomial query complexity with a horrible fraction of errors. It has to be a decent fraction of errors, even though it could be subconstant. And so putting these two components together, one keeps the subpolynomial query complexity, but improves the fraction of errors to constant. Okay, good. So the first component, I won't say very much about this. We want high rate codes with subpolynomial query complexity, which only tolerates the tiny subconstant fraction of errors. And this can be achieved, and this can be done by both multiplicity codes and lifted Reed-Solomon codes. It's one is for it to to achieve the rate, to achieve the to achieve the query complexity, it's just take those codes and increase, tune some parameter to make the fraction of error subconstant, and note that at the same time the query complexity reduces. If one also wants to make it algorithmic and make the running time polynomial in the query complexity, I didn't talk about running times anywhere, but if one wants to do that, then one has to be slightly more careful, but it can all be done, and it's good. On the other hand, this kind of behavior, subpolynomial query complexity with subconstant fraction of errors and high rate, cannot be achieved by Reedmuller codes, and just for the reason that just looking at the parameters of those codes, the moment you want subpolynomial query complexity, the rate of the code has to go subconstant, and once the rate of a code is subconstant, there's nothing you can do to come back from that. It's over. There's no such thing as rate amplification. As far as okay. So I'm not going to say much more about this. There's a theorem about multiplicity codes that says that if you that you can get codes with n to the epsilon query complexity and high rate. You can also tune, which is robust to some constant fraction of errors. You can tune that to reduce the query complexity to subpolynomial and make it robust to a subconstant fraction of errors. Good. Now I'll talk about component 2. This is the more interesting part of the talk. If I may say so myself. So we're talking about, this distance amplification method is called the Alone-Edmonds-Luby distance amplification. It was invented by Alone, Edmonds, and Luby in order to give linear time decodable erasure codes that lie on the singleton bound. And the theorem that, so what it allows us to do is to take the previous theorem, which says that you can get codes with subconstant distance, and just to amplify it a little bit, it says that you can. So note with the change, the decoding time changed slightly. We increased it, we squared it, and this fraction of errors went from subconstant to constant. Okay, and in fact, one can do it so that the rate plus distance is 1 minus epsilon, and the fraction of errors correctable is delta over 2 minus little over 1. Okay, good. And so I'm going to do this in detail right now. Okay, so I'm going to explain what is this transformation on codes that can improve its distance and which can be, and so that at the same, so it improves the distance, and it's also the case that the fraction of errors you can correct locally improves to constant fraction of the distance. Okay, good. So we start with a code word of your original codes. In this case, let's say it's a multiplicity code word. We break it into blocks of constant size. No, not constant size. We break it into blocks of small size. each block we encode using, it's a small size block, we encode it using a small error correcting code with good rate distance trade-off. It doesn't need to have any properties other than it should have good rate and distance trade-off. So for example, Reed-Solomon code is a good choice. Good. So let me list all the code words there. A1, A2, A3. Those are the symbols of the first code word. B1, B2, B3. Those are the symbols of the second code word, and so on. So far what we've done is just concatenation of codes. We took the outer code, the breaking into blocks is some small operation, and then we encoded that with a further with another error correcting code. Okay, now the main transformation happens. We draw a bipartite expander graph with an equal number of vertices on the left and the right, just there adjacent to all these Reed-Solomon code words. The different symbols that are written on a particular let me use the mouse. The different symbols that are written on the different parts of the different symbols on this Reed-Solomon code word are then written on the edges adjacent to that vertex. So every vertex here is associated with the Reed-Solomon code word, and the three symbols here, A1, A2, A3, are written on the three edges going out of this. Okay, if the Reed-Solomon code word is 5,000 characters long, then we should take a degree 5,000 expander graph drawn over here. Okay. Now on the right hand side, okay, so what we're now going to do is on the right hand side for any vertex, we will also, whatever symbols were written on the edge, we send them along the edge to go to the other side. And on the right hand side, you collect all the symbols that got sent to it. For at any given vertex, for example, here we got an A3, a B2, and an F1. So we take those three symbols and we write them down: A3, B2, F1. This is the transformation. Okay, so now we take each such green block and call that a symbol of our alphabet, and good. And this whatever is written on the right hand side, this is the code word of the distance amplified code. Okay, so every code word of the multiplicity code gave you a code word of this distance amplified code. Okay, so I now reason about, I want to reason about this. I want to say that, oh, in fact, if you could correct the multiplicity code word from some tiny fraction, little one fraction of errors, then you can actually correct this distance amplified code from some constant fraction of errors. Any questions about what this operation was? Okay, so just to fix some notation, let's for the Reed-Solomon code, the length of each message. The length of the message part, this I'll call it B, and the length of the code word I'll call it D. Okay, and the distance of the Reed-Solomon encoding, let's call it delta. Okay, so that means these strings all come from Reed-Solomon code of distance delta. Okay, let's first understand the first part of this operation before we use the expander. Okay, and we'll see that this operation allows us to protect from a constant fraction of random errors. Okay, so we'll first study what happens in the case of random errors, and then we'll see what happens in the case of worst case errors, which is what we need to address eventually. Suppose we faced random errors. Okay, so the symbols are independently some delta over 2 fraction minus epsilon fraction of the symbols are randomly chosen and corrupted. Okay, then okay, so we're in good shape because with high probability, so if delta over 2 minus epsilon fraction of random errors occur, with high probability within each block, or in almost all the blocks, only at most delta over 2 fraction errors would have occurred. When less than delta over 2 fraction errors occur in a Reed-Solomon code word, you can correct it because the Reed-Solomon code has a distance delta. So I didn't need to say Reed-Solomon anyway. I could have said any code. But you have a code of distance delta and less than delta over 2 fraction errors occurred, then this is something that can be corrected. So one can correctly decode these symbols. Okay, so 1 minus little o1 of these gray blocks here can be correctly decoded just by looking at, just because the Reed-Solomon code word there can be corrected by itself. A small number of these blocks cannot be correctly decoded, some little o1 fraction of them. This is where the multiplicity code word can come in. So the multiplicity code word can handle a little o1 fraction of errors. So now we go to the original multiplicity code word and we ask it to decode this in original code word, and it can, because it can handle little o1 fraction errors. The important observation about this argument, this is a very simple argument, and it just says that when you have random errors, you can count on each block getting roughly the same fraction errors. So if you can make each block not get too many errors, then you can do the decoding of this kind of concatenated code. Everything here can be done locally. If you want to locally decode this from random errors, one can run the local decoder for the multiplicity code word. Every time it queries a symbol, one would look into the associated. So remember, the code is what's written in the gray blocks, the new code. In order to decode it, one runs the multiplicity code word. Every time it wants to access a symbol, maybe here, one looks into the associated Reed-Solomon code word, sees what's there, decodes it from delta over 2 fraction errors, and gets the candidate symbol for the multiplicity code word. And this whole thing can be done locally. Nothing about this argument was non-local. So given from the multiplicity code word, which can handle little o1 fraction errors, one can instantly get a code which handles delta over 2 minus epsilon fraction random errors with exactly the same query complexity. Okay, now we use the expander, and now we'll use the expander to amplify what we just showed about random errors into worst case errors. So the key point is that, in adversarial errors, so the expander will distribute the adversarial errors from the green side onto the gray side in a very random fashion, and it will be enough for the previous argument to work. Okay, so suppose delta over 2 minus epsilon fraction of the green blocks get corrupted. Okay, then by the expander mixing lemma, almost all vertices on the left-hand side, or almost all the gray blocks, will have at most delta over 2 neighbors amongst the corrupt blocks on the right-hand side. If that happens, oh yeah.
Sorry, Swastik, this is a generic argument now, or it doesn't have anything to do with local decoding or anything. You could
right. So far, it doesn't have anything to do with local decoding. I did mention that the multiplicity code. One could do the random error decoding part locally too. But yes, what I'm proving now will also prove the distance of the code, and that has nothing to do with locality. But the only thing to do is to observe as I do the argument that everything algorithmic that I want to do can also be done locally by querying a few neighbors of the given vertices, etc.
Mm-hmm.
Good. So if delta over 2 minus epsilon fraction of the green blocks are corrupted, then almost all the gray blocks have the property that they do not have too many errors. They do not have too many neighbors amongst the corrupt green blocks, which means that the gray block can be decoded by just doing Reed-Solomon decoding. One does not have to go up to the multiplicity code. Once 1 minus little o1 of the gray blocks can be recovered, the multiplicity code allows you to recover any one symbol of the original multiplicity code word with high probability. the point now is that everything can be done locally. So we're back at this picture. Let me say pointer. Okay, so the local tester, the local decoder for the multiplicity code. So in order to do the final decoding, what one does is one runs the local decoder for the multiplicity code, the local corrector for the multiplicity code. Whenever it wants to access a symbol, we go into the corresponding Reed-Solomon code word and say, I want to access this. But this isn't the code anymore, right? The code is this is all these green blocks. So in order to recover what's written in this particular gray block, one looks at all the neighbors of this gray block. There are some green blocks and queries the relevant symbol from those green blocks. Get those symbols back and collect it into this candidate Reed-Solomon code word. Then decode the Reed-Solomon code word using Reed-Solomon decoding. It's a small instance, so we can just do it anyway. Having decoded it, we get a candidate symbol for the upper multiplicity code word. Send that up, and this is how the algorithm works. So the local corrector for the multiplicity code word has access to all these symbols, and the guarantee is 1 minus little one of them are correct. And this is exactly the promise required for the multiplicity code local corrector to correct, to get any one particular symbol of what it wants correct. So that's everything. So please ask me questions now.
I hate to ask things, but like in terms of efficiency, is it efficient or in terms of time?
Yes, it is time efficient. As long as the multiplicity code decoder is time efficient, all one needs to do here is to do some Reed-Solomon decodings on a very small block size. And also there's some amount of blow up involved in, every time you want to access a symbol, you need to access D symbols from the green blocks. Yeah, so there's some poly and D factors which are polylogarithmic in the runtime. So everything can be done efficiently too. It's not just query complexity.
Okay, so going back and forth in the expander graph actually doesn't cost that much.
Right, it's not so much back and forth. Every time you want to access a symbol, you just query its neighbors. Done. That's it. That's the first source of back and forth. So that's a one-way thing. The other thing is that the local correction question is not about recovering a symbol of the multiplicity code word. It's about recovering a symbol of recovering a green block. So what we really should do is say, I want to recover the green block. So that's the same as that would work if I could recover all its neighboring gray blocks. So then the problem becomes recover all its neighboring gray blocks, and that becomes recovering a small number of symbols from the multiplicity code word. And yeah, so there's some amount of blow up there. That's a factor D, and there's another factor D because every time you want to access a symbol, you need to access D green blocks. So those are the only two blow ups.
Okay, thanks.
Good. Okay, so this is the whole construction. So let me go back and show you the picture. Let's see. Right, so we took the original code word, we Reed-Solomon and broke it into blocks. Reed-Solomon encoded each of them. Then we redistributed the symbols using good expander, and we called each of these new redistributed. We bundled up some of these things and called them code words. Okay. Good. And this can be made to work over the binary alphabet by just concatenating this final green block with a good inner code. So this actually turns out to be a very large alphabet code, but one can concatenate down to binary alphabet, and it becomes a binary locally correctable code. For locally testable codes, let me give a high-level sketch of what the argument is. How much time do I have, by the way?
You're just right out of time, but if you want to take just a couple more minutes, I think it's fine.
Okay, so a couple more minutes. Okay, so the strategy is going to be the same. We're going to construct high-rate locally testable codes with subpolynomial query complexity, but at the cost of subconstant distance, and then we'll do distance amplification, the exact same transformation as before. Okay, and the new query complexity is exactly the same. So I'm not going to talk much about the distance. In fact, I'm not going to talk about the distance amplification here at all. It's exactly the same as what happened before. They were just amplifying the distance and noting that the local testing algorithm can be made to work locally along with that expander graph construction. So how do you construct high rate locally testable codes with subpolynomial query complexity and subconstant distance? So this turns out it can be achieved by tensor codes. If you take a tensor code, and it can also be achieved by lifted resolvent codes, but with weaker parameters. If you take a tensor code with instantiated in a non-standard setting, the reason of non-standard is because it gives you subconstant distance, and nobody ever, I mean, it was illegal to look at subconstant distance before because we didn't consider them legitimate locally testable codes. But it's just a different setting, and it leads to query complexity being 2 to the root log n log n, which is the same as what happened in the case of locally correctable codes. So this is slightly weaker than what I promised. To improve this, we do something different and construct error correcting codes which have better subpolynomial query complexity and subconstant distance by not just tensoring, but by doing something more. So what we do is right. So I mean, the operation of tensoring leads to very sharp declines in the distance of the codes, and this is what is the bottleneck in the previous construction of subpolynomial query complexity, subconstant distance locally testable codes. But instead, what we use a different strategy to construct such codes by alternating tensoring and distance amplification. So this follows some earlier work of Mayer in the constant query locally testable code setting, and it's similar to things like the zigzag product. And it gives a better component one for that locally testable code construction. And this gives us a locally testable code with sub 1 over poly log n distance and query complexity log n to the order log n. So this is what the final query complexity ends up being. Okay, so I probably don't have time to say what this tensoring business is. The main point is tensoring reduces the distance drastically, and so it would help if it didn't reduce it so drastically. So we alternate it with another application of the Alone-Edmonds-Luby distance amplification method. So it brings the distance back up to where it started, and one can tensor it again. So we use log n iterations of tensoring followed by distance amplification, followed by tensoring, followed by distance amplification, etc. There are various technical issues that need to be handled along the way. Some of these issues came up even in Mayer's construction, and we use his solutions. And some problems are unique to this because we use Alone-Edmonds-Luby distance amplification, which is good. So to get codes of the binary alphabet, one just takes these codes and concatenates them down. The rate versus distance trade-off is worse. More recently, along with Sivakant, Gopi, Rafael, Oliveira, Noga Ronzevi, and Shivang Saraf, we were able to use the ideas from this paper to construct locally correctable codes and locally testable codes meeting the Gilbert-Warshaumer bound. So that means it matches the best known. So these codes have the rate distance trade-off matching the best known non-local rate distance trade-off for error correcting codes. And it uses ideas from this paper along with some other ideas of Thomason.
Swastik?
Okay, yeah.
You mean a given alphabet size, right?
This whole slide was for the binary alphabet.
Oh, okay, I missed it. Thanks.
Or I didn't say it, I was racing through. But yes, so this for binary alphabet, one can get the rate distance trade-off matching the Gilbert-Warshaumer one. Good. And yeah, so just to wrap up, there are many very interesting open questions for the constant rate regime. Here are the most important questions for locally decodable codes and locally testable codes. For locally decodable codes, can you achieve poly log n query complexity? For all we know, you can. For locally testable codes, presumably you can even achieve constant query complexity. And another closely related problem is the problem of constructing PCPs with constant rate and low query complexity. Today, we only know For constant rate PCPs, the best query complexity we know is O of n to the epsilon. And on the other hand, with 3 queries, you can get rate 1 over polylog n. Yeah, so it's so everything's very delicately poised, and it would be nice to see what can be done. Okay, that's it.
Thanks, Swastik.
Okay.
So
no clapping.
Well, yeah.
No, it's
There's
okay.
a button somewhere. You can. I forgot. There's a special effects thing that can clap. If I find it, I'll clap later. In the meantime, if there's any questions, some more questions for Swastik, please unmute yourselves and speak up.
So let me.
Okay, well, I have maybe one tiny question. So just in terms of, I think this is something you probably said and that I misunderstood. So you're using the fact that the multiplicity code you start with, so this distance, what you call distance amplification. So it's using that you have a code that can recover from constant fraction of random errors, and you're transforming these into worst case errors. So is that the case?
No, it used slightly more than just that it was random errors. It used the fact that within each block, the number of errors was not more than delta over 2. It's not a black box transformation for random errors to worst case errors, but it is for this pseudo-random property, it is.
Okay, because you're using both a property of behavior of the original code with respect to random errors, but also the fact that it can recover from worst case errors, but it has this bad from sub-constant fraction of worst case errors, right?
Right. Oh, you're saying maybe for recovering from random errors, you don't need the multiplicity code to be able to recover from worst case errors. Maybe it could have been done with just random errors. I think that's correct.
Okay.
Oh, maybe I didn't answer your question.
Partially. I think I don't understand exactly what are the properties of the initial code that you need.
What's the most relevant about it? It's completely black box. So if the outer code is a locally correctable code, which can handle 1 minus little 1 fraction errors, after you do this Alon-Edmonds-Luby transformation with the Reed-Solomon code and the expander redistribution, then the final code is resistant to worst case errors.
So there's no such thing as an assumption about how the initial code behaves with respect to random errors.
No, not at all.
That's just something that's going to hold irrespective. Okay, thanks.
Right, yeah. So we start with the original code, which is resilient to a little over 1 fraction of worst case errors. After you concatenate with these Reed-Solomon codes after breaking to blocks, then it's automatically resilient to random errors, no matter what the original code was. And and then the expander redistribution amplifies it improves it then to resilient to worst case errors.
Thanks.
Wait.
I have a quick question.
Yeah.
So I was wondering if you could say a little bit more about, so you have this improved LTC for sub-constant errors. Can you just say a little bit more about the ingredients that go into that and what the hang-up is, like trying to do the same kind of argument in the LCC or LDC?
So for locally testable codes, we have there are a lot of tools available. They have nice composition properties. As far as I know, for locally correctable codes, one really has to get it in one shot. Why the things I say about locally testable codes cannot be used for locally correctable codes is just because everything doesn't hold. But what are the ingredients?
What the construction was for the LTC.
So for the locally testable code, so we have this operation of tensoring, which so it's what I say is slightly false. But if you have C, which is a locally testable code, then C tensor C, which is the code formed by looking at all matrices, all of whose columns and rows are both code words, are all code words. That's a new code, the tensor code. And if C is locally testable, then C tensor C is also locally testable with basically the same query complexity. While we improve the length of the code from C to C square. And so this is not exactly true, but this is almost true. And so it's a way of increasing the length of a code while not harming the rate too much. If the rate is nearly 1, the rate of the tensor code gets squared and it stays nearly 1. And on the other hand, it does harm the distance quite a bit by if the rate is nearly 1, the distance is nearly 0, and so the distance gets squared, and that makes it even more nearly 0. So this is a bad operation. And so what we do is we alternate that with distance amplification. So the distance amplification brings the distance back up. Okay, maybe nothing on this slide is comprehensible. Okay, so the distance amplification brings the distance back up so that it's ready to be tensored again. And when you bring the distance back up, it doesn't hurt the rate too much. It doesn't hurt anything else too much. And it's still the query complexity is still low because distance amplification preserves local testability. That's roughly the statement of this theorem. So the distance amplification gets used many times in the construction of component 1. Right. So it was anyway the main star of component 2. I mean, component 2 is alone Edmonds-Lobby distance amplification. But component 1, now we use the same distance amplification step many times in order to construct the code for component 1. For locally decodable codes, I basically don't know any operations that you can do with a locally decodable code and still get a locally decodable code other than distance amplification now. But did that answer your question?
Yeah, you can't see them, but I think they said yes. Thumbs up.
Okay, good. Okay.
Thanks. Okay. All right. Any more questions for Swastik?
Oh, the crowd went wild. I didn't realize it was so exhilarating.
So if there's no further questions, I'll soon close the broadcast, but you're all welcome to stick around with Swastik and ask some more questions, but I'll stop the live. Just to remind you that in order to leave enough time for everyone to attend and enjoy Fox, the next talk will take place not in 2 weeks, but in 3 weeks. So we'll have Ron and Eldan from the Weizmann Institute to give the talk. And then the following talk will be just a week after. So we'll resume the usual schedule. So it's just the next talk, which is pushed back 1 week. So thanks for joining us. And we hope to see you in a few weeks. And thanks, Swastik, for giving the talk.
No, thanks.